comments on the Nvidia Earnings Call Q2, August 2024. The stock is down about 6% today after the call, and the reasons for that, in my opinion, are the Blackwell delay and in general just fatigue on the stock. It's up 130 to 140% for the year. So this is not something terribly concerning. I think what we want to talk about today here is really the way we see Nvidia as a company and as a stock and as an investment. It's a large investment in our portfolio, so we take it very seriously. And I think the main pros of why you want to be invested in Nvidia are the reasons that Jensen repeatedly says is the shift towards accelerated computing and the shift towards an all-encompassing architecture, whether it's Hopper or Blackwell, which is the new one, because what you need is you need all the components to fit together. So in a sense, Blackwell is a networked system on its own with, of course, CUDA as a software layer on top of it to help people flexibly adapt to all the new developments in AI. Generally, AI is data and search. So that's something, actually, there's another episode I'm working on for that particular topic. I think it's kind of crystallizing from two different directions that this is the future of AI. One is Francois Chollet's presentation I just spoke about a while ago about AGI, and then there's also Sergey Levine's keynote speak at a summer school. I forgot which one. Links are all in the show note. The key is the following, right? You're going to have to go with data and search. You need both. And the way search works is roughly, to use Sergey's approach, in some way or form, some shape or form, it has to be an optimization problem. In a sense that you have different paths and you want to find the one path that is the most useful given the task that you're given. So why am I talking about this now? I'm going to discuss this in a separate episode. I think it's too important to just sort of mix it together, and also Nvidia's earnings call is too important to have it mixed with a scientific episode. That's why I want to keep it separate, but I find it still interesting to actually, why don't I just put it together? Yeah, this is, I apologize for this. Sometimes these things happen on the go, and that's part of the Not Even On podcast. So we're just going to go together. And the reason we're going to go together is because I think the scientific and the business side really come together very nicely, and this is very important. So what is Jensen saying? Jensen's saying on the call that we have an increased demand for compute. We have a lot of different tasks that are already being shifted towards accelerated compute. And, quote, the Nvidia Blackwell platform brings together multiple GPU, CPU, DPU, NVLink, and link switch, and the networking chip system, and Nvidia CUDA software to power the next generation of AI across the cases, industries, and countries. So what he's saying here is that this is a multitude of different subcomponents that are all morphed into one, and that's the Blackwell architecture. And on the science side, we also have the same drift, which is that the key to AGI, whether it's according to Francois Chollet, who is officially working on AGI, or Sergey's more humble approach towards a more flexible robot, I think they're both going in the same direction, and that is we have data and search. And it's very interesting because Sergey's approach is offline reinforcement learning. That's what he calls search. And he applies it to robots, he applies it to image gen, and he also applies it to large language models. And the way he does it is he's saying we can have a large offline data set that can try to approximate reward functions. And with that reward function, we can then use real data sets and optimize them. So we kind of pre-train a model based on offline reinforcement learning just to learn the reward function. I think that's kind of the way I see it. And on Francois' side, it's he calls it program search. That's a little bit different. I think there are differences here. What Francois is after is more, again, we have data, of course, that helps us find the optimal space, finds out the action space, if you will, and then we need to kind of refine the action space within with either program search or offline reinforcement learning. There's slightly different approaches to the same problem, which is find the most optimal trajectory in a very large data set. This is not even a podcast. It's August 29, 2024. This is Crimdelco. For the year, we're up 3.2%. The market's up 17.3%. We're underperformed by 14.1%. We had a drawdown of almost 10% this week. Started with Tesla, now Nvidia. So we're just crumbling, if you will. Unfortunately, I think we have some issues in the car market in China, and we have the Nvidia earnings call. And that's what we want to talk about today. So let's talk about the Nvidia earnings call. And if we want to tie it together with Francois and with Sergey's presentation. And the reason we want to do that is because we believe that this is one of those rare moments when we see where the rubber meets the road. So we see the business side of things and we see the science side of things. And it's not surprising that Jensen is able to combine those two, because Nvidia is really a very science-driven company in a sense that they look at what's going on in the science world. I mean, just go to GTC. GTC almost looked like Nurex. And then they take all the projects or learnings or problems that arise within the science community, and they solve problems with their network infrastructure. So what Nvidia is really trying to do here is kind of build architecture, they call it Blackwell, that is based on the idea that you want to have as much acceleration across the data center as possible. And you also want to keep it flexible, because you don't know what the workloads are going to be in the future. This is very akin to, let's say, what Tesla is doing with Dojo. Like, Tesla is trying to optimize Dojo for video data and video transformers and tokenization and problems that arise from a video-driven learning method. And Nvidia wants to capture that, but also many other methods of learning. So Nvidia wants to keep it general, but it also has to be efficient. And it's about cost per token. In the end, it's about cost per token. And if you want to go one step further, it's cost per solution. I have a problem. How can I best train my model to deliver a solution to the problem, whether it's predicting movies for customers on Netflix, or whether it's solving a grasping technique for a robot? In the end, they're all very similar problems. We need a lot of data, and then we need an optimization path that helps us get the most optimal path within the large set of possibilities. Call it the possibility space. So the possibility space is covered by data. The more data we have about a certain task, the better we know what the possible approaches are towards solving that task. And then we have to find a way to optimize. And the best way we can optimize, I'm using Sergey's approach here of offline reinforcement learning, is kind of the idea that we could have learn a reward function based on the task, so predicated on the task. And then when we get a new task, we can then use that reward function and maybe use online reinforcement learning. So in the moment, have a model that, given that it knows the reward function, can optimize the robots or the AI's trajectory. So that's kind of the way we understand it. These things are a lot more complex, of course, than a 15-20-minute episode can cover. But that's kind of where we stand on the science side. I want to say a few more things about science, and then I want to switch to the Nvidia call. Again, they're tied together. So on the science side, we have sort of the trifecta of what AGI could look like. One is we have large-scale data sets, then we have self-supervised learning, and then we have flexible models in general, flexible in general. So we want to have a large data set. We want to have some sort of self-supervised learning within the large data set that allows us to sort of check out the action space. And then we have large general models that can help us optimize within that space. That's kind of the way I understand Sergey's presentation. And what that helps us to do is build a flexible system, which means that a robot can potentially, on the fly, learn how to solve tasks sort of in a zero-shot general way. That's the idea in robotics. And again, it doesn't have to be a robot. It could be a recommendation engine that is exposed to, let's say, a new client that wants to, have movies recommended on Netflix. And if you can efficiently recommend some good movies for her, she is new. She lives in Iceland, and you don't know much about her, but you have a few data points, and you have a reward function that you've learned in offline reinforcement learning while optimizing in this particular case. What's the difference between offline reinforcement learning and reinforcement learning with human feedback is that within offline reinforcement learning, what you're doing is you're looking at a lot of possible reward functions, and then you're optimizing, hopefully, a reward function for your given task. Reinforcement learning with human feedback, that is, you're learning from specialty, special people or special agents, what their preferences are, and then you're imitating those preferences. So it's not as scalable as offline reinforcement learning. Now, why am I talking about all this within the context of the Nvidia earnings call? I think this is the key question here, right? And the answer to that question is that we have a convergence of large data-driven models with the necessity to find optimization techniques or search techniques to find the most optimal trajectory within those large data sets. I mean, that's really the combination. And that is, in my opinion, also the key in NVIDIA's earnings call. And I want to talk about the call in the rest of this episode. What that means is that we have a new a new problem statement, right? That's the key. There's a new problem statement. I think Jensen is trying to bring that across. There's a new problem statement. It's large data with search. And you can attack this in many different ways. And one of them, of course, is Blackwell. And then Blackwell is a new architecture that is designed by NVIDIA. And, there's a lot of technicalities. There's network cards and networking and CUDA and GPU and CPU and data processing units and all that kind of stuff. But that's not really what interests us as investors. What interests us as investors in the context of NVIDIA is really there's a new problem statement. And the statement is, how can we combine data with search the most optimal way? In Richard Sutton's famous essay, The Bitter Lesson, Sutton talks about the idea that we shouldn't be teaching AIs how humans think. That's not the idea, because we don't know how we think. So we shouldn't be teaching anybody about how we think when we don't know. But one thing we know is that large data sets combined with search work. And that's really what Sutton is saying. So it's not that bitter of a lesson, in my opinion. And people are, of course, dramatizing this essay. But that's not the problem. I think what Jensen is doing is he's restating the problem set, and he's on the he's on the right track here, because Francois Chollet's presentation about AGI this summer in Seattle at the AGI conference, and Sergey's presentation, again, they're all in the show notes. They really talk about the same thing. And I think those are two researchers that I personally take very seriously. And I think the community is going to follow them. And not just because they're great people, but because they're, it's working. It's going to work. I think we've seen this in robotics. We've seen this in robotics. We believe that hopefully Tesla is using some of these techniques now for the self-drive and also for the humanoid. And again, what are the techniques? Well, you have a large data set of humans that have done the task. And you combine a large data set of tasks, let's say driving, right? And then you have a robot that is cleaning, and then a robot that is making scrambled eggs, and so on and so forth. And you put that data set together. That's the data set. That is the action space. That is what is possible. But now you want to optimize a trajectory for a robot that maybe is deployed in just driving you around, right? A self-drive robot taxi. What is the key here is that you optimize for that specific task, and you can do that in Sergey's case. He's talking about offline reinforcement learning. So what he is saying is that we can learn a reward function for that particular driving task, and then given the knowledge that the car has about its actuators and the model that he's trained on, he should be able, it should be able to drive you around, and it will do that better if it's trained on a more general model, but which also incorporates things like scrambled eggs and cleaning, because we have transfer learning and we have the navigation problem as the key within robotics. For large language models, this is a different task, but it's in a sense very similar. Again, we have the body of text that is available on the internet, which is the data, the action space, but then we have the specific trajectories for, let's say, writing a nice PR piece for Boeing because they just screwed up, a space mission. We could use offline reinforcement. In other words, we could use search to find the optimal trajectory within all the possible spaces that exist that we could write. We find the optimal trajectory. What's the difference? Take this example of a large language model writing a piece of text, right? The way sort of traditional, maybe ChatGPT-4 and less works is we have sort of a maximum likelihood method approach, which is, okay, given all the body of text, what's the most likely output of text that I could give given the prompt? This is how I would say, probably generation 1 of Gen AI works. And I think this new approach that Sergey and Francois are both trying to get at from different angles is that, well, we still want to have all the possible, the action space, so we need all the data, but now how can we better optimally, how can we optimize the trajectory? How can we find the optimal text? And maybe it shouldn't just be a statistical most likely scenario, but maybe we could have a more subtle approach where we have, let's say a reward function that is learned on, given this type of prompt, this is more likely to be driven in this direction versus that direction, based on the prior, which is that offline reinforcement learning. Or in Francois Chollet's world, it would be more, okay, we want to search in program space. Now we have all the data. So we have, let's say, all the text in the world that has been written. The prompt is, I want to start this sentence with a Cormac McCarthy style, a couple of sentences, and then continue with maybe less Cormac McCarthy and a bit more Scott Fitzgerald, something like that. Within that context, now I'm going to have a program which is trained to deliver that particular style of writing, and I can optimize the trajectory more efficiently than if I just statistically do what's more probable given the prompt. So I hope
I'm able to explain this. These are very subtle differences, but they're subtle in sort of in English explaining it, but I think they're very, very different when it comes to the implementation on the metal itself. So when we train these models, the way we train them, the way we execute them, I think it is going to grow exponentially in terms of the data requirements on both sides, the sort of action-based data, and also if we use Sergey's approach, the online reinforcement learning is going to be very, very data intensive. So we need a lot of data, not just to have the action space understood, but also to have the trajectory planning optimized. The more data we have in offline reinforcement learning, the better we can approximate the most optimal trajectory, and therefore the better our models will be. So to summarize, I think this is a very nice example of how science and technology are coming together. And I think the key message of this, if there's one thing I want listeners to take away here, is simply that Jensen is restating the problem statement of AI. It is data and search. This is Richard Sutton, the bitter lesson. This is Sergey Levine, this is Francois Chollet. All of these people are all in line. It is data and search. And for that, Nvidia is building this new platform, Blackwell. And I think for us investors, the main concern on Wall Street when it comes to Nvidia is well, you've been growing so much. How far can this go? What's competition going to do? You have 84% of the data center spend already. The new spend, can you continue this? And what Jensen is saying is yes, because it is going to keep growing. The pie is going to keep growing. And we are the leaders because we're the cost leaders. We're the cost leaders. We are the best cost-efficient solution. And that's why we can deliver this kind of growth with these kinds of margins. That's what he's saying. And it's up to us investors, of course, to calibrate this, particularly the margin side of things. The reason Nvidia has such high margins is because they're able to deliver 10x value at much, much lower cost per. Okay? It's not absolute, it's per. Cost per solution, cost per token. That's why Nvidia is so successful, and that's why we believe it's going to continue. Now, of course, they're not going to grow 3x every year. That's not going to happen. The key for us investors, of course, is to look a little bit at the numbers, not too much. We don't want to be boggled down with ROIs and things like that. Simply because in a growth situation like that, this is not very useful. But what we want to look is, of course, we want to look at, let's say, a 5-8 year type trajectory in terms of free cash flow generation, like something along those lines. I think that makes a lot more sense for a growth company like Nvidia, because it's not very if you've been growing 3x this year, next year you're only growing 2x. I mean, what exactly does that mean? And what does that mean? You should lower your growth G in your formula or something like that. I don't think it's necessary to be that specific, but we want to still have a sense for valuation. I mean, the purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. So this is a good example of how you want to think about this. And again, do your own research. Please don't take this as an investment advice or anything like that. All we want to say is the following, that we have a certain expectations for growth. In our case, it's about a 30% CAGR for the next 5 years. We give the company about a 35 PE after those 5 years. And we come up with, given a discount factor and all these kinds of things. And I don't want to go into details, but we come roughly with a $130 price target, given all that. So we're very close to the market, and I think the market is pretty reasonable in pricing something like this. 30% growth is a lot. That's very, very much. That's more than Amazon had with cloud and Microsoft and all these big software-driven companies. They didn't grow that much over a long period of time. So you need a sort of a secular shift in the problem statement, and that's what Jensen's talking about. We have this new way of combining more with more, so data with more search, and then on top of that, we have just all these other use cases, whether it's data analysis, recommender systems, Gen AI, the new frontier model,
you know, the CIA doing stuff with Palantir for terrorism research. There's just all these tasks that all are morphing into the same type of problem: more data and more search, and whether it's to, you know, offline reinforcement learning or program search, or that's not even that key. What's key is fundamentally finding a way to generate much more solutions per cost, per dollar, or per token, or more tokens per dollar. This is the key. And Nvidia is the leader in this space, and that's why we're invested. Hopefully this has helped. I think, again, Jensen is keeping it very simple. There's a new problem statement. We have the architecture to deliver, and we're going to grow with the market. Thank you.